hyperconjugation. Resonance and hyperconjugation. Little bit we have discussed about resonance. What is resonance? That is multiple structure that can be, we can imagine, we can draw, okay, which is scientifically logical. It should be logical. Logical some structure. Multiple number of such structures representing the same molecule. And these structures, some of them can be more stable, some of them can be less stable. Those who are more stable, they are more contributing, and those who are less stable, they are less contributing. Resonance structures sometimes can be drawn, but may not be contributing. That means this actually does not occur. Okay, so some rough idea with one example I can give you. What is this compound name? What is this compound? What is this compound? Acid. Acetate. Okay, acetic acid corresponding anion. So acetate. Now, if you have a resonance structure, these two structures practically not different. But if you mark this oxygen, if you mark the oxygen, this oxygen and this oxygen, if you mark, they will not be the same. This is suppose oxygen 6 and atomic number is 12, 13, 14. So if I take another one, some other isotopes of oxygen. So you can understand that this structure are not same. Though looking same, but actually not same. Two different structures. Both the structures are equally stable. Both the structures are equally stable, and they are called, they are resonance stabilized, giving quite good stability. That's why this is acidic, because it can easily release H plus. Why? Because the acetate ion, weak acid corresponding anion, that is stabilized by resonance. That's why they can easily release H plus. So that's why acidic. Now if you take phenoxide, last day I have discussed phenoxide, that alcohol is neutral, but phenoxide is making the phenol acidic. Phenol is acidic, but alcohol is neutral. Why? Because phenol, the corresponding anion phenoxide is resonance stabilized, but alcohol, the corresponding anion like sodium ethoxide, it is not stabilized by resonance. That's why it is not so acidic. Phenol is acidic because phenoxide is stable. Alcohol is not acidic because alkoxide is not stable. Am I clear? If the language is clear, please concentrate. If you take acetic acid, why it is acidic? Because acetate ion is stable by this resonance. Phenol is acidic. Why? Because phenoxide ion is stable by resonance. Alcohol is not acidic because alkoxide is not stabilized by resonance. Sulfuric acid is acidic because sulfate ion is stable by resonance. Nitric acid is same reason actually. Organic, inorganic, everywhere is the same. If somehow or the other way the anion is getting stabilized, the corresponding acid will be strong acid. Now,
so here the bottom ion is more stable.
No, both are same, equal. Actually, there is no difference between the two structures. They are called equivalent structures.
But sir, if you consider the inductive effect?
No, I am not considering inductive effect. I am talking about the resonance. So these two particular molecules, it will be equally stable. These two structures that I have drawn, both are equally stable. Okay, they are equally stable. Now, I am not comparing with plus I and minus I. If there is another molecule which is different, then only you can compare that way. But here both are acetate ion. Both are same ion, only the resonance I am showing. Okay, and it is getting stabilized by this resonance, and so it is acidic. Effect of resonance when we discuss, and that is the another one. That inductive effect phenomena is different. There you have to compare like acetic acid and chloroacetic acid, acetic acid and formic acid. If you compare, then the concept of inductive effect comes. But here it is acetic acid only, not two different molecules. Same molecule, but only the resonance is solved. Now hyperconjugation. So as this resonance we have already, maybe we will be discussing later again. So now here what you can see in the PowerPoint, it is hyperconjugation. Now what is hyperconjugation? First of all, you need to understand what is conjugation. Then only you can understand hyperconjugation. Conjugation is if you have two alternate double bonds, the pi electron is getting distributed in between the carbon molecules. So there is a flow of electron and called conjugation. That is also a resonance, but some special type of resonance. It is also a resonance. Like for example, you take butadiene, two double bonds alternately placed. Okay, where is the double bond placed? Carbon number 1 and carbon number 3. 1 and 2 and 3, 4. So there are two double bonds, consecutive double bonds, adjacent carbon. So in this case, the electron, there is a continuous overall overlap between the all the atoms involved in the molecule. That is called conjugation. Let me draw it. Now what is conjugation? Something like this. This is butadiene. Now we can draw like this. What are these? What are the drawing indicates? Pipe. This is one pipe and this is another pipe. Now the molecule is rotating, means carbon-carbon single bond always can be rotated against each other. So carbon-carbon single bond against the carbon-carbon single bond, rotation is quite easy. Slowly, easily, and it is rotating itself without any provocation or external agency. By its own energy, internal energy, it is rotating. All molecules are like that, either vibrating or rotating or moving around. Okay, if it is a gas, moving around in the whole container. If it is a solid, then there is a vibration. If there is a liquid, there is rotation as well as vibration and all sorts of movement possible. So different type of such movements are, so molecules are rotating like this. But by rotation, sometimes it may happen that these and these are becoming parallel. Possible, that's a possibility. That by rotation, they can sometimes become parallel also. So there is a overlap between the two also. That's the most stable structure out of this, all these different type of structures that can be drawn. Here, this also can be overlapped together. So the electron distribution is totally distributed throughout the molecule. It can be flown, electron is flowing inside the whole molecule. It is not localized in a particular carbon, but sort of delocalization. And resonance is nothing but delocalization of electron. So here it is delocalization of electron going on. And this structure, if you consider particularly, this is called conjugation. Delocalization of molecule, resonance. But this resonance is something, well, different type of resonance is there. This is one type of resonance, we are calling it conjugation. Resonance is general term. It can happen in so many places. But whenever it is happening in alternative double bonds, we are calling it conjugation. And it's called pi-pi conjugation. Pi-pi conjugation, because both are pi terms. And what is the difference? How do you understand? Ordinary double bonds molecules and this type of conjugated double bond molecules, if you compare their stability, you will understand this is becoming more stable. This is giving some more stability. Okay, because of more delocalization of electron by resonance. This is called conjugation. So now conjugation. And here what I am showing here, it is called hyper. What is the meaning of hyper? The term hyper means what? Something more, something extra. Something extra. Hypo means something less. Hyper means something more. So hyper conjugation is something more than the conjugation. Now you understood what is conjugation. So now hyper means sigma pi conjugation. Earlier it was pi pi. So conjugation is pi pi. And sigma pi conjugation is called hyperconjugation, which is present here. This is sigma bond, this is pi bond, and in between sigma and pi there is a conjugation. So this is what? This is CH bond. CH3. CH3 means C and H. C and H, C and H. This CH3 and this double bond pi bond, there is a conjugation between the two, which is called hyperconjugation. Sigma pi conjugation. This is called hyperconjugation. Normally we are calling conjugation means pi pi conjugation, and here it is a sigma and pi, that's why we call it hyperconjugation. So what is the importance of this hyperconjugation? Sometimes it gives stability to two carbocation, two double bonded molecules. Okay, it is sometimes more stable compared to our expectation. Okay, that is called hyperconjugation. Hyperconjugation is a phenomena which is not very strong. If you compare all the different phenomena or effects, resonance is the most effective, giving stability by resonance. So resonance is the most effective among all these effects. Among all the effects, resonance is the topmost, most prominent. If resonance is there, in good quantity resonance may not be always there. Maybe you are expecting there is resonance, but because of size factor, resonance may not be good. Like chlorine is very big size compared to carbon. So that's why, though there is a lone pair on chlorine, chlorobenzene, there is not a good resonance that is happening. Okay? Because chlorine is a big structure, size, and carbon comparatively much smaller. So big and small, this combination is not good. That's why resonance is not happening that much. You may show that there is a lone pair on chlorine. You can show it that chlorine copper lone pair. There is a lone pair on chlorine, so resonance will occur. You can draw also, but practically it is not happening. Why? Because chlorine is large size and carbon is small size. There is no compatibility. But if you take oxygen, lone pair on oxygen, and there is a double bonded molecule, so there will be resonance, good amount of resonance. Okay, and if resonance actually exists, it will overcome all the other effects. If really it exists, not fictitious, really if it exists, it will overcome all the other factors. So that is the topmost one. Second one is coming inductive. Inductive effect is second position. I am talking about the effects of different type of effects. Now then, hyperconjugation. Hyperconjugation coming later. So if there is a inductive hyperconjugation resonance, all the factors there, we can compare this way. So hyperconjugation is coming later. Why coming later? Because here practically sigma bond is very rigid. So sigma pi conjugation, if I show also, it will not be that contributing. इतना होगा नहीं, जितना हम लोग सोचा था उतना एक्चुअली होगा नहीं. हम लोग दिखा सकते कि हो रहा है, राइट, लेकिन उतना नहीं होगा. Contribution is less because sigma is rigid, so it cannot go that if this overlap as you are showing, that overlap is not that great extent. It is happening very small quantity. If it happens actually, it happens in a very small quantity. That's why it is coming in the third category. First is resonance, second inductive, and third coming hyperconjugation. Now why it is coming third? Because sigma pi conjugation is not as good as pi pi conjugation. Sigma is rigid, it is not so flexible, so it will not give the electron towards the resonance that much. It is also a sort of resonance. Sigma pi conjugation is also called one type of resonance. This by resonance also you can show the hyperconjugation. Okay, so this is one way of showing the hyperconjugation. So what is the importance of hyperconjugation here? This CH3 group is giving stability to this carbocation generated. This is a carbocation CH2 plus, CH3 CH2 plus. What is the name of the compound species? CH3 CH2 plus means ethylium ion, ethyl carbocation, okay. CH3 2 carbon, methyl 1 carbon, ethyl 2 carbon, so CH3 CH2 plus, ethyl carbocation. This ethyl carbocation getting stabilized by the hyperconjugation over here. What is the importance of hyperconjugation? What is the application of hyperconjugation? That I am showing here. It is giving some sort of stability by this, by this sort of overlap.
Here inductive effect is also possible.
Yeah, that is there. Another effect I am showing. I am not ignoring inductive. Inductive is there, and along with that, this effect is also there. Now, कोথায় পাই বন্ড হচ্ছে सिग्मा एंड पाई देयर इज ए कॉन्जुगेशन सिग्मा बॉन्ड अपना जगह पे उसके साथ एडिशनल कुछ कर रहा है अपना बॉन्ड तोड़ के नहीं जैसा है वैसे ही अच्छा नाउ व्हाट आई कैन शो यू कार्बन you can write like this also just for illustration I am showing you this okay hyperconjugation hyperconjugation. So it is also a sort of resonance. That's why I am giving the resonance symbol. Okay. So H plus here, H, double bond, this. As I show the resonance, the same way showing here. Now your question comes, how it is breaking? Actually, we are showing this way, not practically breaking. Not practically breaking. We are showing it that way, that some sort of delocalization is also happening here, involving the sigma bond, but that involvement is very little. If you say it is involvement, that involvement is very little. It's not that much involved that it will really break. But how we can show people? We are showing the people like this way. So, and if it happens, it will happen 10 to the power 24 times per second. So actually not measurable. It is so fast, catching immediately. If it breaks, it is catching immediately. It will not give you H plus as like acid. That H plus is not detectable. The right language is detectable. You cannot detect that particular H plus form. No bond resonance. Yes, it is also here, so I need not write in the board. You see here that structure is happening, breaking this way. Not only carbocation, it is giving stability to alkene also. So this is another factor. Third one, not very prominent, but in the third one I can keep it. No bond resonance. That's also a factor. It is called hyperconjugation. Hyper means more, and conjugation means delocalization among the conjugated double bonds. Delocalization among the conjugated double bonds is called conjugation, and if it happens between sigma and pi, then it is hyperconjugation. If it happens between only pi, then it is conjugation. Methyl is least stable because it is prime. This is zero. It is called 0, and this is 1 degree, 2 degree, 3 degree. 0 degree, 1 degree, 2 degree, 3 degree. 0 degree means methyl, 1 degree means primary carbocation, 2 degree means secondary carbocation, and 3 degree means tertiary carbocation. Now, what is the difference here? Inductivity is there. Along with that, some application of hyperconjugation is also there. But I can tell you why actually hyperconjugation happening. CH3, there hydrogen carbon is attached to 3 hydrogen. Now hydrogen is very very small. That's why the CH bond, which is very small bond, the CH bond is very small bond. The electron density is getting forming a cloud over the carbon. Carbon ka upar. It is forming a cloud over the carbon. So that much of electron density this carbon cannot hold because it is electropositive in nature. That's why it is donating. This language I think I have used earlier also.
Yes, sir. Inductive effect.
Yes. The same thing is happening here also because of the same phenomena. Because carbon cannot hold that much of electrons, so it is undergoing some sort of no bond resonance. It is giving inductive effect. Electron density is so high, it cannot hold that much. That's why it is giving. So that's why it is most stable for inductive as well as for hyperconjugation. It's a combination. Now, if it is in opposite direction, then obviously inductive weight will be stronger. But if it is in the same direction, it can enhance. It is happening always in the same direction. That's why enhanced. So this is radical. So far I was showing you carbocation. Now here radical, methyl radical, ethyl radical, propyl. By the way, inductive effect can explain the stability of carbocation. It can enhance the stability of carbocation, and we can explain also with the help of inductive effect. Okay, this one is more stable, this is primary, this is secondary, secondary is more stable. We can talk that way. But whenever radical comes, we cannot explain with the help of inductive effect because radical is not cation. There is no plus charge. And if there is no plus charge, inductive effect has no role towards the stability. That's why hyperconjugation take an active role over here. What is the importance of hyperconjugation? Now you will understand. Inductive effect is restricted for only carbocation, not for radical. But hyperconjugation is applicable for radical also. This radical is least stable, this is most stable radical, this is secondary radical which is most stable, and tertiary radical is the most stable. More stable, and most stable. What is happening? Why the stability is increasing with hyperconjugation or how? by some resonance again, we can show the resonance. Okay, we can show the resonance. The same resonance type of structure, resonance structures. This is free radical, ethyl free radical, C2H5 dot. Now it can undergo resonance like this, which is again no bond resonance. How? This is giving here, this is giving here, and one here. So here it is becoming H dot, this is becoming a double bond, and this is my structure. So the same way, you don't expect that H dot and H dot will join give you H2. That will not occur here, because immediately it will be recaptured. If you just think that it is giving H dot, immediately it will be recaptured, and these three, all the hydrogens there are equal. That's why this can happen to any hydrogen. So how many structures you can draw? 3 structures. The more the number of such structures that can be imagined, more will be the stability. The more the probability of structures, number of structure means number of probability. So it will be more and more stable. So this one has no such hyperconjugation phenomena. Here there are 3. Here there are 6 structures, and this hyperconjugation happens. The adjacent carbon. How many number of hydrogen attached to the adjacent carbon? That is called alpha hydrogen. So this alpha hydrogen matters. Here alpha hydrogen is only 3, so 3 structures can be drawn. Here it is 6, so 6 structures, and here it is 9, so 9 structures. That's why it is getting stabilized. So apart from inductive effect, it also has got importance, because the radical cannot be stabilized by inductive effect, so it can be stabilized by hyperconjugation. So it also has got importance.
Sir, how the radical form?
Radicals form in the, there are 2 types of mechanism. You have seen Markovnikov addition reaction. They are ionic mechanism, and anti-Markovnikov addition reaction, there it is happening by radical mechanism. Okay, the radicals are triggered by some sort of peroxides. If you apply peroxide, that is called initiator. That initiates the radical. It can be, it can produce atom also. Atom can act as a radical, means similar phenomena. Like one very good example, you have already in the class 9-10 standard heard about this chlorination of methane. Chlorination of methane. So methane plus chlorine in presence of sunlight, diffuse sunlight particularly, producing methyl chloride, methylene chloride, chloroform carbonate chloride, step by step. So what is the process? What is the mechanism behind it? First of all, chlorine is getting atomized, producing Cl dot. So it is acting just like radical. Cl dot and any radical, methyl radical, behaving similar. So let's take example Cl dot. That Cl dot is knocking methane, producing methyl HCl and methyl radical. Not methyl chloride, HCl and methyl radical. Okay, if you make methyl chloride, H dot is produced. That is not possible, because H dot has got no stability. So what will happen? It will form HCl plus CH3 dot. Then in the next step, CH3 dot will knock another chlorine molecule, producing CH3Cl plus Cl dot. So your Cl dot is reproduced. You are getting it back like a catalyst. Again it will attack, go on again, and ultimately you are getting different reactions, methyl chloride, methyl chloride. What is the mechanism then? Chlorine atom. Atomized chlorine, right? Atomized chlorine. So similarly, I can show you so many cases how radicals are formed. CH3 CO, OOCO CH3. Okay. It is called par acids. CH3CO whole 2. Okay. CH3CO OOCO CH3. CH3CO OOCO CH3. Par acid. Okay, these par acids, whenever bring in presence of sunlight or any type of some little bit of heat, it breaks into CH3CO. CH3COO. So that is the formation radical. First radical is formed. Different of radicals are formed. Acha, bromine. Oh, bromine again like chlorine. So nothing different. Let's take other
So
example.
my question is why?
Why? It is actually oxygen bond whenever there. It is very much unstable because oxygen has got lone pair. So lone pair and bond pair they are repelling a lot. That's why they are already unstable. So a little bit of energy can easily break it.
So they form O minus. Why it is radicals?
No, not O minus. Not possible to form O minus. I'm talking about like this. You have ROOR. Here there is a lone pair. Here there is a lone pair. This is lone pair bond pair interaction. Here lone pair bond pair interaction. This lone pair bond pair interaction is making the bond very very weak. And then whenever sunlight exposure there, it breaks into two RO dots. H2O2, it breaks so easily. Why? Unstable. Why unstable? Oxygen bond is quite weak, and weak bond can be easily broken with little bit of heat or light energy. So it can be chemical or photochemical. If you are giving heat, then chemical. If you are giving light, then photochemical. So it breaks into radical. So radical mechanism occurs. So in case of Markovnikov addition, it is ionic mechanism. That means first H plus is getting added, then Br minus. HBr addition. You take example, propene plus HBr. What you are getting? CH3, CHBr, CH3. That means number 2 carbon you are getting methyl. CH3, CHBr, CH3 you are getting. Right? So that is called Markovnikov addition. But if you give in presence of peroxide you do the reaction, then it will undergo radical mechanism. Anti-Markovnikov, that is going by radical mechanism. Why radical is formed? You get the answer there. Radical is forming there. Peroxide is present. That is initiating the radical. Once it is initiated, it will undergo propagation and termination. Initiation, propagation, termination. Initiation means starting. Propagation means forward reaction going on, and after that termination means getting ended up. These 3 steps are there in the radical mechanism. But in case of ionic mechanism, you have only cation and anion. Cation is getting added, then anion is getting added. The entire mechanism is different, and that's why product also are getting different. Markovnikov product and anti-Markovnikov product is different because of this phenomenon. Your mechanism entirely different. Okay. If required, I can show you. First of all, let me finish this. Okay. So this is all. Then application of hyperconjugation. This is not substituted, so less stable. More and more substitution giving more and more stability. The more substitution, it is giving more stability because alpha hydrogen present. It is giving hyperconjugative stability. Here there is no hyperconjugative hydrogen, alpha hydrogen not there. Here there is alpha hydrogen present, that's why it is giving some stability. There are both sides you have what? Alpha hydrogen present, that's why you are getting more stability and so on. More the substitution, more is the stability because of hyperconjugation. Here you cannot give the inductive effect phenomena because double bond, how it will be stabilized by inductive effect? Inductive effect can give stability to cation, not to anything else. But hyperconjugation is much more widely applicable. It is applicable for stability of the radical. It is applicable for the stability of the double bonded molecule itself. Otherwise you cannot explain. Just see why this should be more stable compared to this. Why this will be more stable compared to this? How? Cannot give any explanation until unless you apply the concept of your hyperconjugation. So hyperconjugation is giving the stability to olefins, as well as you can explain the stability to radicals. Acha, one thing. Primary radical and secondary radical. Secondary radical is found to be more stable. You know, don't know that primary is less stable compared to secondary radical. That you cannot explain with the help of any inductive effect on it. There you can explain this in terms of hyperconjugation. You can explain the stability with the help of hyperconjugation. Okay.
Hey everyone, Professor Davis here again to talk to you a little bit about hyperconjugation, specifically how it applies to carbocations.
Primary and secondary.
So carbocations are most stable and more substituted.
Primary and secondary?
Radical.
Okay. Primary and secondary. Primary, for example, this one is a primary radical and this one is a secondary radical. just এটা হচ্ছে একটু গন্ডগোল হয়ে গেল। This second. Another hydrogen replaced by methyl is becoming tertiary.
So secondary is more stable, no?
More stable because of more hyperconjugated hydrogen. This one.
You know this from our
Oh, acha, jabe.
And we also know that alkyl groups are weakly electron donating. That's the mechanism by which they stabilize carbocations. Because reducing or delocalizing charges in small organics gives those ions greater stability. So we expect methyl carbocations to be very rare, so unstable. Primary is not much better.
So as I was discussing, the same thing is there here. Just see.
In tertiary carbocations, we see these constantly in organic chemistry. These are staples of first-order substitution and elimination reactions. And the reason is that alkyl groups are increasing the stability of.
So this is methyl. Primary means one is hydrogen is replaced by one alkyl group. Two hydrogen replaced by two alkyl groups. It is secondary. And three alkyl groups are hydrogens are replaced by alkyl groups. It is tertiary. And the more the substitution, may not be methyl. More the substitution, maybe ethyl, anything. So in that case, your inductive effect is increasing as well as hyperconjugation is increasing. Inductive effect and hyperconjugation most of the time in the same direction.
But in the alkyl group is CH3 then?
Yeah, alkyl group CH3 means it is also alkyl group, no? So it is giving inductive effect as well as hyperconjugation. So how many, if it is CH3, then how many alpha hydrogen? 9. So it is giving more stability. Compared to here you are getting 6. Here you are getting 6, but here you are getting 9. So it is giving more stability. And inductive, if you see, here you are getting plus I effect of 2 methyl group, and here you are getting 3 methyl group. So this is supposed to be more stable. So both what I am telling, inductive effect and hyperconjugation, both are working in the same direction most of the time. And if it is in opposite direction, if it happens by chance, then inductive effect will win, because inductive effect is stronger compared to hyperconjugation. But hyperconjugation is much more widely applicable compared to inductive effect. Inductive effect is only offering one stability factor, that is to the carbocation. But this hyperconjugation is applicable for so many things.
Of the carbocation. So let's take a look at what it is about these R groups that allows them to donate electrons, put electrons close to that carbocation center. So here I've drawn for you the methyl cation and the ethyl cation. And these two carbocations you're not really going to see in a genuinely bona fide reaction because they're just not stable enough. But they're the simplest examples that will allow me to demonstrate how hyperconjugation works. So let's set aside the fact that these are unreasonably unstable and just take a look at them right now anyway. So I'm going to turn them into three-dimensional representations, and then I'm going to turn these representations on their side. And when I do this, I can place the unoccupied p orbital on each carbocation center.
This is actually model, you see. This one is what? CH3 plus, and here it is CH3 CH2 plus.
Center vertically in the plane of our page. Now, what's different between the ethyl and methyl cations is that the ethyl cation has a neighboring CH sigma bonding molecular orbital. And this bonding molecular orbital is actually filled with electrons.
This is vacant orbital.
Onto the hydrogen.
And this is
But we
free.
also know that these electrons, though I've drawn them here in between the two bonded atoms, we know that they actually have free run of that entire volume that is defined by the molecular orbital. So they can run all around, up and down. And as you notice, occasionally they find their way.
See, the electrons are moving around here and there. That way you are just thinking. The delocalization of electron, no? Electron is jumping from this filled cell to the empty or vacant cell here. So it can roam around into this small vicinity. It is not very long. This carbon-carbon distance is small. So they are just jumping around here and there, this particular area. That's why there is some sort of overlap, you can think of overlap. Electron cloud is spreaded up to this region. That way you can think.
Over to the empty p orbital on the carbocation.
Happening like this
And
practically.
when this happens, they slightly attenuate the positive charge, thereby decreasing. And remember what we said previously. Anything that
Animation is nice though.
localizes
You can
charge
understand very
in
well.
small organic molecules
Actually how it is happening.
is going to stabilize them. So this is why having additional alkyl groups around the carbocation center makes them more stable and therefore more likely to form. So next time we'll talk a little bit about how this hyperconjugation and the stabilizing effect of alkyl groups on carbocations leads to things like hydro.
Electron has a tendency that whenever it gets empty space, it fills that also. Like gas has a tendency, if you have some empty room, it fills itself there. So here, whenever there is a vacant orbital, electron is roaming around, and that is actually hyperconjugation. This is what? This is sigma bond, and this is empty p orbital. So whenever empty p orbital available into very close vicinity, the electron is roaming around, just jumping around here and there. But within this small range, not very long distance. Okay, that can happen, and that happens. Right?
And I'll see you then.
Okay. Application of hyperconjugation. So application also I told you, but this is also another way of showing the hyperconjugation. That is by in terms of resonance. What I have shown in animation that you cannot show in the exam, na? That you can for understanding is fine, but how will you write in the exam? You will write it that way. This is also another way of representation. You have to use this representation when you are writing the pen paper. You don't have animation there, you can use this. Okay, so your H plus, this H is getting involved, this CH bonds is broken temporarily, and immediately the next one, and this one is getting joined again.
Yeah, another structure is also possible.
This third one is also possible, etc. You can, that's why. Okay, so application of hyperconjugation in case of methyl benzene. What is that called? Toluene. Methyl benzene is toluene, right? So this toluene. Toluene is also showing the hyperconjugative stability. Here, this stability, you just see, if you just tell it the inductive effect, that cannot explain. By this sort of stability, hyperconjugation also can be applicable. Next topic is reaction intermediates. Carbocation structure, planar structure, just overview. Already you know this. Carbon bearing positive charge called carbocation, getting stabilized by resonance, inductive effect, hyperconjugation, and solvent stabilization. 4 factors. Number 1, resonance. Number 2, inductive effect. Number 3, hyperconjugation. Number 4, solvent stabilization. If there is a polar solvent, it will give stability to the carbocation. So these are the 4 factors present for a carbocation. Carbanion is a pyramidal structure. Carbocation is a planar structure, sp2 hybridized. And carbanion, sp3. It is pyramidal structure, just like ammonia. This structure is like ammonia. Now, this is stabilized by what? Resonance, no hyperconjugation. Resonance, inductive, minus I effect, and hyperconjugation not possible. Then solvent stabilization. That means 3 factors. 3 stabilizing factors can be possible. Minus R effect, minus I effect, then you have solvent stabilization.
Why not the hyperconjugation?
H minus we will have to show, which is not possible.
Minus.
H plus possible, but H minus is not. That's why you cannot show hyper. And particularly if it is happening in the non-aqueous medium, anyway. So H minus has got very little stability, that you know. Hydrogen ion has got stability, but hydride ion, it is least stable.
তাহলে স্যার কোনো কার্বোক্যাটায়নের ক্ষেত্রে এটা কনসিডার হবে না।
না, হাইপারকনজুগেশনটা হবে, কার্বন আয়নের ক্ষেত্রে হবে। Then free radical, top view and side view, free radical structure. Now there can be 2 structures possible for radical. One can be sp3 hybridized, and one sp3 bond is occupied by a single electron, or otherwise there can be a sp2 hybridization and one electron will reside into a pure p orbital. These 2 possibilities, and both are available, both are happening, both are right, none of them are wrong. One is sp3 hybridization, one sp3 bond is occupied by a single electron, structure I am talking about. Or the otherwise sp2 hybridization and one pure p orbital occupying one single electron, structure of free radical. And they are called triplet state and singlet state. Okay, triplet and singlet radical. These two types of radical are there. Now, comparative structures: methyl cation, methyl radical, methyl anion. Just see, have a look. Methyl cation, planar. Methyl radical. These two, if you ignore, because pure P, empty, one electron. So you can consider this also sp2, and this is pure P, sp2 and pure P, and this is vacant P, and here it is filled by a lone pair. That's why it will be pyramidal. The structure will be pyramidal, not planar. sp3 means it will be tetrahedral, but if one position is not occupied, then pyramidal. Just go through very fast. These things already I have shown you earlier. That upper one is phenol and the bottom one is nitrobenzene. Here you have plus R and minus I effect, and here you have minus I and minus R effect. Just repetition. Okay. This is what? Benzyl carbocation. Benzylium ion or benzyl carbocation. Double bond, this is CH2 plus on the benzene. That is called benzyl ion carbocation or benzylium ion. Undergoes resonance stability. This is more stable, most acidic. This is less. Acidity decreases in this series. Depends what are the groups present. NO2 group has minus I minus R, making this more acidic. There is no such group present, so less acidic. There is CH3 giving plus I effect, less acidic. OH group is having plus R effect, least acidic. This is inductive effect, plus I effect, stability of carbocation, stability of carbon ion together, plus I and minus I, all otherwise resonance. Acidity order of carboxylic acid, this way we can. And another thing, basicity order. If you have a plus I effect, the basicity increases. So this is the most basic, this is less, this is less. Least. So I have completed in time.